Good morning or good afternoon, depending on where you are. My name is Kathy Kroll. I'm the co-director of technology transfer for the IBT ABC UTC at Florida International University. I'll be moderating today's webinar, and I'm assisted by Dr. Ankitha Arvan, who's a research professor at FIU who will be monitoring the web room. Thank you for your help, Ankitha. Our director is Dr. Atorad Azizanamini. Dr. Azizanamini sends his regards and his regrets for not being with us today. He had a conflict with an NCHRP meeting. Dr. Azizanamini has requested that I remind everyone about our 2024 World Bridge Engineering Conference that will be held in Miami, Florida on December 11th through the 13th. The call for abstracts is currently open. Please go to our website for additional information and to submit your one-page abstract. Please note, with the expanded focus of our UTC to include both accelerated bridge construction and innovative bridge technology focus, the breadth of our topic for this year's conference has expanded. Please go to our website to see examples of conference topics. We hope to see many of you at the conference as attendees, presenters, and exhibitors. Now I'd like to share some of our upcoming events. The Precast Prestressed Concrete Institute will be holding their 2024 convention in Denver, Colorado from February 6th through the 9th. That's rapidly coming up. For more information and registration, please use the link provided or contact William Nickus at the link on the screen or the email. Additionally, the AISC and SBA, the American Segmental Bridge Institute, and the National Steel Bridge Alliance will be holding their World Bridge Symposium in conjunction with the NASCC Steel Bridge Conference in San Antonio, Texas from March 20th through the 22nd. Again, for additional information and for contact information, there are links and email addresses for your use on the screen. For the IBT ABC UTC, our next event is the quarterly research seminar to be held next Friday, January 26th from 1 to 2:15 Eastern Standard Time. We'll be exploring fiber reinforced concrete for accelerated bridge construction applications. This research has been undertaken by our colleagues at the University of Washington. Dr. Travis Thonstad is the principal investigator and will be joined by Carolyn Donahue. Our next monthly webinar will be February 15th from 1 to 2:15 Eastern Standard Time. We'll be talking about the implementation of the new specifications for the National Bridge Inventory, SNBI. Idaho Transportation Department will be joining us to share their implementation planning. We'll be joined by Mike Johnson, the State Bridge Engineer, Alan Burig, the State Asset Management Engineer, Patty Fish, who's implementing the plan as the Bridge Asset Management Project Manager, and we'll also be joined by Rob Schmidt and Zach Boyle from Mayview to give us additional insights. Now we'll get to today's webinar. We'll be discussing building bridges at the speed of segmental. We're joined by Matthew Adams, who's a senior lead bridge engineer at Corven Engineering, which is an H&H company, Hardesty and Hanover. We will be having a question and answer session immediately following the presentation. Paul Lyles, who's the former bridge engineer, state bridge engineer in Georgia, will be moderating the question and answer. And Jugesh Kapoor, who is the director of bridges and structures at HNTB, will also be helping with moderation. So we welcome Matt, and I will turn the presentation over to you. Thank you very much for joining us.
Okay, thank you, Kathy. Thank you for that introduction. I am Matt Adams with H&H, and I am pleased to be here with you today to present on building bridges at the speed of segmental. And so before we get started here, just to address some segmental bridge basics. What is a segmental bridge? So a bridge that is segmented in short length and constructed one piece at a time. The segments are match cast connected to provide a completed span. And what that means is the segments either cast in place using moving form travelers, in which the segments are progressively cast adjacent to the previously cast segment, or they are precast off-site using forms, and the segments are cast again progressively against each other and then separated at the casting yard, shipped to the erection site, and then reassembled to maintain that same joint alignment. The segments are typically concrete box structures providing full bridge depth sections, including the top deck. And so that's really what makes it unique, is that the girder itself with the top deck is cast in one piece, comprising the full girder cross section. And then that's going to be then assembled jointly together to complete your spans. The segments that are cast can either provide the full bridge cross section width, or for wider bridge sections, that can be done in individual pieces and connected transversely together once at the erection site. So why would your project choose segmental construction? And so one of the reasons we're here today is the benefits that it offers for accelerated bridge construction. It provides a repetitive process for efficient construction, and the constructing the full bridge section minimizes forming and finishing work at the construction site. You may utilize them in complex site and environmental constraint conditions, and the segmental solution can provide a reduced footprint and offer top-down construction in these occasions. It may also find the use for economical long span bridges, and they're particularly well suited for elevated viaducts and rail transit bridges. The narrow piers and the narrow girder soffits require minimal clearance in confined areas, so bridges can be built in the medians of existing right-of-way. And the bridges can also follow the curvature of the rail. And so in transit bridges, the rails can be positioned directly over the webs, reducing the demand on the top deck and making for a more efficient structure. They also offer improved elevated aesthetics if that's a desire for your project. So ABC and segmental bridge construction, how do they fit together? So the mission of ABC is to reduce the societal cost of bridge construction by reducing the duration of work zones, focusing special attention on preservation, service life, construction cost, education of the profession, safety, and development of a next generation workforce fully equipped with ABC knowledge. So an important component of that is reducing the duration of work zones. And so the less time that the traveling public is impacted, then that provides a benefit to the traveler, reduce costs, and potentially even improve revenue for the owners. Precast segmental construction can meet these objectives by providing rapid precast segmental erection techniques, reduce the construction footprint, which thereby reduces the impact of travel lanes and disruption to the traveling public. And special erection methods can be implemented to reduce traffic closure durations, so that the operations can be performed at night or during weekends, during minimal hours, and the facilities reopen during peak travel times. The Federal Highway Administration Accelerated Bridge Construction Manual states that the precast segmental construction can be considered an ABC method because faster than cast in place segmental construction. And I would further to that it's faster than cast in place bridge construction. And here we get an overview of the general segmental bridge types, and there's principally two methods used for segmental construction. There's the cast in place balance cantilever and precast balance cantilever methods. And then the other is the precast span by span method. The remaining methods are really variations of these two primary methods. And unidirectional cantilever method is a variation of the balance cantilever, in which the same procedures are implemented. It's just done in one direction only. Incremental and progressive launched is similar to span by span method, where the bridge is assembled at the end of the bridge and then launched into position. Cable stay and extrados bridges are a variation of the balance cantilever method, in which segments are erected first to the piers and then progressively out from the piers in a balanced fashion. And then unique applications of segmental construction are arch construction, as well as precast segmental substructure. One thing I'd particularly like to point out in the photo on the right is, as we look at the different methods being utilized, on the left side of that image is a traditional cast in place concrete structure constructed on false work. And to the right side is the extrados precast segmental bridge construction. And transitioning from one to the other, you can see the congestion that's created by the false work supports. And so when you're trying to minimize work zone impacts, and implications to the public below. You can visualize here the open space that's created by the top-down construction of the Extrados Bridge in comparison to the cast-in-place on falsework method used on the left side of that image. Now, when does precast segmental make sense? So precast segmental can be an on or off-site prefabrication of segments, and it can be done in a controlled environment in a casting yard. This offers improved quality control, so segments can be inspected and rejected prior to erection. This is particularly important in this case because if you have a issue that occurs during casting of the segment, if there's a concrete pump issue, delivery issue, the material's not as intended, or a defect occurs during casting, that segment can be separated and disposed of and rejected and replaced prior to being implemented into the final structure at the erection site. It's a lot harder to do when you're actually at the erection site and build a piece and it does not conform to the project and has to be removed. So significant advantage of this is also that it can be protected from weather. And so as you see here in the photograph, this was a project in Minnesota that required year-round casting, and the weather could not accommodate that. So casting these segments was performed indoors in a controlled environment that the temperature could be controlled and provide better access for the workers. And then after casting, the segments were then taken out on rails out of the building into storage prior to being transported to the erection site. The precasting provides a repetitive factory production process, and so you're replicating the same procedure every day with all the equipment where you want it, and you're able to keep everything organized and repetitive. And so it reduces errors that can occur, improves efficiency, and improves safety. And as we speak to safety, one significant advantage of precasting segments is that in this controlled environment, you're low to the ground. You're in an environment you normally work in, and can control that situation much more easily than you can out on a erection site. Also offers expedited construction and can reduce traffic and construction impacts at the site. Another advantage of this is that if your project is in a rural area and you have a difficult time getting laborers to that site for fabrication of the bridge, is that the precast yard can be set up off-site in a location that is more readily available for your workforce. So some considerations for precasting segments is that depending on the transportation and hauling restrictions, your girder depth may be limited. If you're hauling on traditional highway routes or through town, the size of the segment has to be limited to fit within the confines of that hauling route. And so you often have segment limitations that are 10 feet deep. And using those segment depths, you can achieve spans up to 275 feet using the balanced cantilever method. If the casting yard is on the water and your project is on the water and you have barge access from the casting yard to the project site, allowing barge delivery of the segments, then that reduces some of the restrictions that you have on the size of the segment. And in that case, larger segments can be transported, supporting up to 450 feet for balanced cantilever construction and precast method, and then up to 1,250 feet for cable stay bridges and precast concrete construction. There is economy and scale, and so this is often a question that comes up. We've seen projects about 200 segments or more to be economical, unless other conditions influence the cost. And so what we find is that if there are specific conditions that warrant the use of segmental or top-down construction, in which other access to the site would be more costly, you can have segmental bridges with less than 200 segments. But it does have to consider the fact that you do need the forms for the casting of those segments. But again, it's a scale issue, and so you can also accomplish that with smaller casting yards, fewer beds for operation of that project, and so that reduces the upfront cost of some of the formwork required. Or you can also have situations in which the contractor has those forms already, or a precaster is able to provide those segments for the project and doesn't need the additional upfront costs that's associated with the contractor providing that. So significant aspect of it is standard details improve economy, and simple designs lead to savings. If every segment being cast, you have to change the forms out, remove panels, to accommodate different attachments inside of the segments. That adds to the cost and reduces the efficiency and speed in which those segments can be produced. And again, segment precasting may be performed by the contractor or a precaster. And so sometimes the contractor elects to set up the yard and provide this operation. And occasionally they'll also have precasters that'll provide this service for them. And it's just part of the normal operation. They can get the precast forms for the segments, and then their operation is similar to they would be doing for a precast beam. So a segment casting yard here that we look at, this is a typical layout for a project that was about 2,000 segments. So you do have the casting operation itself. This can be off-site, or it can be directly adjacent to the site or near the laydown yard, depending on where the project is located. It can be hundreds of miles away if the project necessitates that, depending on its location and where you want to cast the segments from. Typically, it's close by because you do want to have the ability to transport those segments readily from the casting yard to the erection site. Casting operations, so as we look at it here, you've got delivery of the equipment to the casting yard, and the operation is there's a reinforcing that's pre-installed in a jig, which is really just a frame set up to mimic the shape of the segment, and so you can pre-assemble that cage. The cage is then picked and flown into the forms and lowered in. All post-tension embedded items are installed then in that form. And a core form is inserted from the rear. What that core form does is create the shape of the inside of the segment. So creates the shape of the segment and incorporates any of the blisters and blocks needed for erection and in-service conditions of that segment. Concrete then is delivered and poured, usually ready-mix trucks. Occasionally there will be casting yards that set up their own batch plant on site, depending on the quantity of segments and access to concrete delivery. And then once concrete's poured, hardened, forms are removed. So the core form is collapsed and extracted from the rear. Softened forms are lowered, and the segment is then advanced out into match casting position. The typical cycle for precasting operations like this is a one-day turn cycle. So every single day you're turning a segment. The segment's reinforcing cage is installed, segment's cast. Next day that segment advances into position for match casting, and the subsequent segment behind it is cast. And you can repeat these operations on a daily cycle. So then after match casting, that segment is then moved out into storage, waiting for transport to the erection site. Some standard precast segment handling. So your typical segment when you're dealing with segments that are transported on the highways, you're usually dealing with something in the range of 10 feet tall and 10 feet long. That works out to common value of about 70 tons, 70 U.S. tons on a weight, 140 to 150,000 pounds. In the casting yard, slings are used to handle these segments using a straddle carrier, and you can see that in that top right image. It's an easy way to just suspend that segment with the slings from the straddle carrier, lift it off the ground, and then move that throughout the yard and onto the trailers for transport. Once it gets to the erection site, though, that segment has to be erected adjacent to the previously erected segment, and the slings would prevent those segments from coming into contact with one another. And so at that location, you've got sleeves or holes cast into the top deck. PT bars are inserted through those sleeves, and a frame is attached to the top that the erection equipment can use to pick that segment and adjust it, manipulate it into position for erection. Another alternative is embedded PT bars. The disadvantage there is that you lose that material every segment that you cast, and as well as PT strands and lifting loops that you're accustomed to seeing in precast girder construction. Now we look a little bit at the bridge construction equipment that is used for segmental bridges and how this equipment can help reduce work zone impacts. And so the image here you see is a location in Tampa where all the equipment was used as shown. Just didn't all happen at the same time, and so you get variations as far as when that equipment was used, but is a representative of the equipment that was used at each location. And so typical equipment is your ground-based or barge-mounted cranes, which is typical to any bridge construction. Use of false work towers and stability props Stability props primarily used in balanced cantilever construction to stabilize out of balance moments. And then you have specialized equipment, which include the underslung truss and an overhead gantry, lifting frames, and mobile lifters, which we'll talk more about. And here we look at the span-by-span method, which was the predominant method used, especially in rapid construction for segmental bridges. In this application, it is literally what the name means. Spans are erected one span at a time, and so the bridge is completed span by span. The full span of segments is supported from the erection equipment that you're using. And so in this application, depending on the various type of equipment you use, the entire every segment's delivered to the site for that span is suspended from the equipment or put on top of the equipment, and is aligned and connected to each other. They can have alignment closures at the end or not. Alignment closures are really just in place, cast in place closures that are usually fairly small, 6-9 inches. And those closures are used to close any gaps that may remain at the end of it to make connections between your bridges to meet the specific location that you're trying to satisfy. The PT is installed and stressed in that span, and the span is now self-supporting, so it can be released from the false work. That span is complete, and or the false work of the erection equipment can then be advanced on to the next location. This method can be used for simple or continuous spans, and can be accomplished with up to 7 spans completed per week. And I put a asterisk, question mark, asterisk here, because that is something that can be done, has been done, but it's not an average. That was a peak rate in which span by span erection was completed. If you're looking at averages, much more common to be talking about anywhere from 1 to 3 spans per week on average, 1 being fairly conservative and 3 being fairly accelerated operation of erecting and advancing completion of spans. And so I would not use the 7 spans per week as a model for anticipating construction durations. So one method that can be used for the span by span, one type of equipment, is the false work support. And so this is a very conventional system. It's not typically been applied in the segmental bridges, but obviously used throughout bridge construction elsewhere. These are segments that are erected by ground-paced cranes, and they're set on false work towers and assembled together. And then the advantage of this system is that you can provide multiple headings with non-linear sequence, and it accommodates bridge geometry. So the curvature of the bridge doesn't require a corded support of a piece of erection equipment trying to suspend that curvature. The false work towers can be aligned as needed to fit the geometry of the bridge. Segments brought to the site and erected onto those tower legs and assembled, and creates a fairly easy operation, fairly conventional operation for this assembly of segments. It does require site access and well-graded, stable soils. And so that is one area which is a little bit contrary to what we're talking about limiting work zone impacts. However, the trade-off is that this can be done very rapidly. And so you're minimizing the amount of time that you're on site by utilizing this method. And it does require you to have full control of that site. And so it is one trade-off. One project that utilized this was the I-5920 Central Business District bridges in Birmingham, Alabama. This project had over 1 million square feet of deck, and that included 2,316 precast segments. There's 4 girder lines, each about 1.25 miles long. And so you see that in the photograph to the right, how those girders were assembled, and then the right 2 girders and the left 2 girders are connected with longitudinal closures to provide full eastbound and westbound directions of this interstate system. The typical span length is 165 feet and 172 total spans for the project. It was delivered using the traditional design bid build method and had a winning bid price of $195 million. Because of the commitment of Alabama Department of Transportation to the public as they were replacing this interstate system in their downtown Birmingham, there was an incentive of $250,000 per day, up to $15 million for early completion. Likewise, there was a disincentive for late completion of $250 per day. That disincentive had no cap. Now, why was Segmental chosen for this project? it was determined to be the only option that could be completed within a 12-month shutdown. So that was one of the criteria from the Alabama Department of Transportation. Was the schedule was actually a 14-month duration with a desired 12-month duration. So the incentive was to get to the 12-month shutdown, and this was determined to be the only method that could be utilized for this project to accomplish that. It did minimize the duration of interstate closure by offsite prefabrication and rapid construction methods, increase the span lengths for the community, reduce noise, and improve aesthetics. Here we see the project timeline, which is really the key to how this project was successful. And so in May of 2017, the project was awarded. A few days later, notice to proceed. And then in October, the substructure work began. And what was important here is the substructure work for this project was actually being constructed under the existing facility. In February, began segment casting operation. And what's really important about this timeline is the entire left half of this timeline is actually performed prior to the clock starting. And so in January 18th of 2019, the interstate was closed, which started the clock for the construction duration. 3 days later, contractor began demolition of the existing facility. Approximately 6 weeks later, the very first segment was erected. So from beginning demolition of the existing facility to completing the substructure, to installing the false work, to erecting the segment, about 6 weeks. About a week later, demolition of the entire facility had been completed. And then in August of 2019, the contractor had completed casting. And that's an important milestone on any project. And it's important to plan that work so that it occurs prior to needing that last segment for erection. So you need curing time, typically 28 days. You want segments anywhere from 14-day minimum to 28 days to have been cast prior to erecting. But you also don't want to end casting too soon, because you'll create too much backlog and too much inventory into your yard, and you'll run out of room for storing those segments. So there's always a balance between precasting the segments and delivering those segments to the erection site, erecting them in time to relieve space in the yard for storage, but also have the segments delivered in time for erecting. And on January 17th, 364 days after the interstate was closed, the entire facility was open to traffic. This provided the contractor the full $15 million incentive bonus. Now, how was this accomplished? Here you see the girder construction, and this is parallel girder alignments with the supported false work. The girder you see on the left has been assembled on that false work, and alignment closures performed, spans stressed, span then becomes self-supporting, and that false work's lowered. It is then side shifted over to its parallel girder alignment for the erection that it's occurring in that position. And you can see behind the false work, the columns, pier columns that are in place for the subsequent third and fourth girder lines that'll make up the westbound corridor. This was really accomplished by using light, easy to maneuver equipment. And so you can see on the right, by having individual towers that were easy to side shift and relocate, the contractor could move this equipment throughout the project site and really work around any constraints that he encountered to allow this to happen. Now, how did this really happen? So we have all segments from first segment to last segment erected. 2,316 segments erected in 217 days, and that's over 10 segments a day. On average, from start to finish of segment erection. It's also at a rate of nearly a span per day on average. And to accomplish this rate, you think of the premium cost that's going to result in, and you look at the bid price for that project. That project was completed at $195 a square feet, which was very competitive with other alternatives, throughout the industry at the time. Further to that, the $15 million incentive to the contractor was sufficient for them to perform that work and accelerate that project by the 60 days. So every activity he took into consideration was whether it was going to cost him more than $250,000 or whether he could make money on $250,000 to accelerate that each day that he had activity, and that was enough incentive to accelerate it. So when you look at these durations as averages, there's a lot of variation that occurs from startup to the project to the end of the project. You hit peak duration at different times, but it was really accomplished. And what was key to this was it was at peak production, it was performed using 8 headings. And so there was not a span on the project that was completed in a day. There was not a particular location in which 10 segments were completed in a day. But on average, that was a production rate using, at the maximum output, 8 headings. The project originated with 1 and 2 headings to start up, built up to 6 headings, and then eventually to 8 headings to hit these production rates. Another type of erection equipment when we look at span by span construction is the underslung truss. And so this really provides the exact same function as what you're doing with the falsework towers, except this would be a situation in which you don't have good access underneath the bridge to place falsework towers. And so here you can see this is over water, and it does not facilitate the location of falsework directly underneath your bridge. And so an underslung truss is used, which is launching girders, which is temporary there. These can be either self-launching or advanced by crane. In the self-launching application, you have the nose that you can see here advancing out, cantilevering out in front of the support on the left, the main girder line, which supports the segments, and then behind it, there's a tail. And these allow the piece of equipment to be launched progressively from one span to the next. As the span's completed, this equipment is lowered, advanced forward, the nose out there in front catches the support ahead of it. As it does that, the rear support is released, advanced onto the next pier, moved into position, and as that tail comes off the backside. If one limitation here is you really need primarily linear construction, and so you don't have the flexibility with this piece of equipment to move from position to position. It needs to move progressively along the length of the bridge, and it's best suited for long, continuous straight sections with supports founded on the piers. The importance of the straight section is that if you encounter this in a curved condition, and you're a curved bridge alignment, is that your equipment is fundamentally courting that length. And so as you work your way around a curved length, a curved alignment, and the equipment starts to chord that section, you're going to run into situations in which you can't make that rotation. The tail's going to run into your box, or it's going to swing out too wide past where the wing supports can accommodate anything on that tail. And so you need to have something that's fundamentally straight or limited curve to utilize this type of equipment. You can reduce that requirement by removing the nose and tail, and then using a crane to suspend the front of the equipment and a hook on the back to support the back of the segment during launching operations. Very similar operation here is the overhead gantry, and so similar situation, self-launching. This can move the supports with it, so it sits on top of the bridge instead of below the bridge as it's constructing it. Really does provide that top-down construction method. Segments can be delivered, just like in the underslung truss, can be delivered from the rear, from the previously completed spans, delivered to the segment, or they can be delivered beneath the gantry itself and hoisted into position. This, because it does operate on top of the box, on top of the structure, has more flexibility when it comes to handling curvature and alignments. It is able to navigate those more easily, but it is still limited in how much it can accommodate in a curvature. So very tight curvatures might require an articulating nose or tail to accommodate that geometry. It's also a large piece of equipment, so relocating it from one location to another, as far as on your project site itself, is lengthy. Assembly is lengthy. It is expensive. You're talking probably somewhere in the range of $5 million for this piece of equipment, and so you do want to make sure and consider that in the upfront cost. However, one trade-off when you're looking at any of these pieces of equipment is that they are replacing, in many cases, the use of cranes that would have to be required, or other false work systems, and so there is something it's replacing that has cost as well. And so it's not just a standalone cost. Here we do look at the articulating overhead gantry, and so this is a more complicated piece of equipment. You can see here as it operates through, it can navigate curvature better, suspend the segments from the overhead. It is more complicated to use. It is more expensive, and obviously, like any piece of equipment, critical stability checks have to be performed at every stage of operation. One way to avoid this, if you do have the real estate on the project site, is to basically have false work towers that serve as outriggers to facilitate the movement. Both this and the overhead gantry that is not articulating. Another advantage of it here you see in the photograph is that it is particularly well suited for parallel girder erection, in which the gantry, the equipment, can side launch as well as launch longitudinally. It can side launch between girder alignments, and so as you're progressing along, particularly in an application like this, which was a transit rail system with parallel girder alignments, is that it can erect a right girder alignment, side launch, erect a left girder alignment, recenter, advance to the next pier, and repeat that operation along the L. Now we look at the other primary method of constructing segmental bridges, and this is the balanced cantilever method. And similar to span by span being reflective of how it's built, balanced cantilever is reflective of how it's built. You start at the pier with the segments, and you progressively build out from the pier in a balanced cantilever fashion. And so you would be erecting a downstation segment and a matching upstation segment that balances that downstation segment. And you progressively do this along the length of the cantilever, erecting segments on both sides to maintain a balanced condition. There is false work required. That's often provided at the pier, supported on the permanent foundation. It's a wraparound out of balance false work system, or alternatively can be provided using a stability prop out on the cantilever that provides that resistance to overturning. Standard cycles you can expect here is typically one pair of segments every day. And so that's a downstation and upstation balancing segment can be expected every day. Those segments are erected and cantilever tendons installed through those segments to secure them into position prior to erecting the next pair of segments. That can be increased on projects up to 2 or 3 pairs per day if there is incentive for the contractor to do that. One particular thing to note on this photograph on the right is that how this application is being used on this interchange. And so this is a new construction of an interchange in Tampa at the Leroy Selman Expressway. And what you see is that with utilizing this construction method, the segments are able to be erected starting, the piers are located in the median fundamentally of that facility. And erection is able to progress out from that median location. And there's some specialized equipment there, which is the orange equipment on one of the cantilevers being actively constructed just off the side of the highway. And that equipment was used at this location because trying to mobilize and locate a crane on this section would have resulted in lane closures, significant lane closures. And this is a tolled facility that generates revenue for the Tampa Hillsborough Expressway Authority. So that was not really an acceptable alternative. And so the utilizing this equipment was able to allow traffic to be maintained under these bridges as they were being constructed during daylight peak travel times, and the bridge themselves were being erected at night closures and weekend closures as needed. The equipment was needed because the cranes trying to move cranes out onto the highway, move them across, get them in position, erect a segment, and then move them back out could not be performed in a night closure. Here we do see a similar application, but the crane construction is being used, and this is this is a ground-based crane erecting cantilever segments. And you can see here on the cantilever on the left, this was previously completed while the traffic was shifted more towards the right, where the crane mast can be seen in the photograph behind the barrier. Once that cantilever was completed, the alignment of the road was temporarily shifted back underneath that cantilever, so the cantilever you see on the right could then be progressed using crane erection. And so it is important to note that while this activity is occurring over traffic, segments are not actively being erected over live traffic. This is either done during night closures, or in this case, as the traffic has been shifted out of the envelope of those segments being erected. And segments are supported by the crane until the temporary PT bars are installed. And once the balancing segment is erected, the cantilevers are installed and stressed, and that pair of segments are complete. Here we look at another method of the balanced cantilever equipment that can be utilized. And this really reduces the need for cranes in this situation. So these kind of mimic what the crane would be doing, but when you don't have the footprint for cranes and access to get the cranes out of position, this is a beam and winch or a lifting frame that attaches to the top of the previously erected segment. As it erects segments, it advances out onto those segments that it previously erected for erecting the next segment. This particular piece of equipment does require the segments to be delivered directly underneath or very close to directly underneath where they will be lifted or hoisted into position, because the cables running down to pick that segment are in a fairly fixed location. One important note is if you're anticipating that your project will need equipment like this, is that the design of these segments needs to consider the weight of that equipment in your design. And so this will often weigh as much as a segment and result in additional post-tensioning required in those cantilevers during erection. Next, we look at another piece of equipment for balanced cantilever erection, which is the mobile segment lifter, which fundamentally operates very much like the beam and winch or lifting frame, except the advantage to this piece of equipment is it can actually pick a segment and travel along the length of the cantilever. And so what you see here is a segment being delivered over a railroad. It was delivered back further closer to the pier and lifted by the equipment, and then can travel out into position. It travels to the end of the cantilever, locks down, advances the segments forward, hoists it into position, and then the segment is attached to the end of the cantilever. This was done using pairs, and so you can see we've got on both sides of the cantilever segments being erected. Generally, the equipment is used in coordination with each other to keep them within similar limits along the length of the cantilever to maintain your balance given the weight of the segments. So if you do have a piece of equipment and you don't have a balancing one, you've got to account for that either with counterweights or stipulated prop, as you can see in this photograph here. Mobile lifter, again, going back to reduction of impact to your work zone. Here you see them being used at a railroad. And so this was another project, and the segment delivered again back by the pier, lifted, hoisted by the piece of equipment, travels along the length of the cantilever, locks down, and advances that into position. So when you've got a crossing, you're building a bridge over a rail corridor, the ability to move a crane out across there, get into position, pick a segment, deliver a segment, pick a segment, install that segment, fouls the tracks, and is often a requirement of the railroad that you're not able to construct in that environment. And so this provides one solution in which either during a temporary outage or service disruption to the line, is that the segment can be delivered outside the right-of-way of the rail, and then hoisted and delivered out and erected prior to service being restored. You see a similar operation on the right side. So this is back again, equipment being used to erect segments over the roadway. Again, not erected during active traffic. This equipment was left in this position from the previous night shift. Traffic was then open that morning, operates throughout the day, and then during the subsequent night shift, segment will be delivered and installed and continue on this cantilever method. Last one we talk about here is the overhead gantry, and so this is very similar to what was used for the span by span, except the primary difference here is that the equipment only has to support one segment at a time, and so it's picking a segment either from behind or from below, brings it up, and then it can move it to the up station or down station. And this is advantageous in situations in which crane access would be really prohibitive in a site, and you can really go back to this top-down construction and limiting the footprint and work. Now we'll touch a little on precast segmental substructures. So this is another system that's used to accelerate the process, very similar to what we do in the superstructure construction. Segments are precast in a casting yard, either on-site or off-site, match cast against each other, and then separated, stored, delivered to the site, and erected to recreate what had been done in the casting yard. You can see here an application that was used in a marine environment, as well as on the right, a situation in which the segment, this was the 5920 project, precasting these in advance of demolition of the structure, really saved them a lot of time. And so that was something that the contractor had developed and proposed, it was really advantageous to that project. And you can see here when they have the entire corridor shut down and they're doing a replacement of the interstate system. This is the construction of the pier columns. And as they were constructing these, since they had the foundations in place prior to demolition, the delivery of the segments was primarily in two pieces. The segmental bridges, since the geometry is handled in the girder itself and not in the piers, are very repetitive. And so you just have a standard cap shape and a standard column shape. And the only variation is in the height of the column, which is accommodated in the straight portion of these precast elements. And so you have two pieces cast, and the contractor utilizing this method was installing approximately 20 pier columns every week at this project site, preparing for erection of these girders. So some lessons learned as we look at this type of method, particularly when you're trying to make sure that you're able to achieve accelerated construction, is to solve the problem before it occurs. And so ABC projects require a commitment from all parties. And what may be a standard solution that you're accustomed to on a typical project may not be appropriate for this particular application. Simple designs and details lead to efficient construction. Something we often say is if it's hard to draw, it's going to be harder to build. So if you're really struggling to put something down on a piece of paper, just imagine what it's going to take out in the field to try and get that done, which adds to cost and adds to the duration. So figure out how the bridge will be built first, then design and detail it. We often find that the actual construction of the project dictates the type of design and what needs to be built. Maybe not the most efficient design, but if it's the most efficient construction, it provides cost savings to the owner. We always want to leave room in the design for construction. So we all want to be efficient with our designs, but things do happen during construction, and having some flexibility or some additional capacity often results in savings in the field when things don't go the way that you want them to. And have a plan for when things don't go as planned. Anticipate issues that may occur and know how to address them ahead of time. Fairly easy to say. This is where your experience from your previous projects really can pay dividends on the next project you're looking at. So you can realize what things did happen, try and address them in the designs, make sure there's a plan in place for when they do happen, if they do happen, so that you don't have a lengthy shutdown that affects your overall. Simple details for rapid construction. And so here are just a couple of examples. Having access to tendon stressing from outside the bridge just makes a repetitive process easier to work with, and gives you better access than trying to get inside the bridge and having to stress tendons from that position. And then utilizing details like you see on the right, external tendons passing through diablos and deviator segments. Keep everything external, prevent blocked ducts, and limit the amount of issues you encounter during construction. So if it's an option when you're looking at your designs, incorporating some simple standard details that provide more flexibility for the contractor can certainly pay dividends during construction. So in summary, segmental bridges can provide a durable, redundant, efficient, and elegant solution to a project when well designed and constructed. But it is important to note that one size does not fit all, and each project has unique requirements. But there are many options available to satisfy those needs. So just because you may have seen a project that was a segmental bridge and you saw it constructed a certain way, doesn't mean that that's the right fit for the next project. There are a multitude of ways of doing it, and each one has its unique benefits. At this time, we did conclude here with some references, and so we've got, for more information, included some links here, both to ABC and UTC, as well as the American Segmental Bridge Institute, and some links to videos that were incorporated from ABC to address segmental bridge construction, and some seminars that were provided as well. Some of those are fairly outdated. You can see over 10 years old, but they still contain some very good information and some of the best practices. So at that time, I am available for questions if we'd like to turn to that.
Thank you very much for that presentation, Matt. Paul, would you like to proceed with the question and answers?
Sure thing, Kathy. And Matt, real good. And we do have a few questions that have come in, and some came in beforehand. So with that, I'll go ahead and get underway. And then it's 1:52, so we'll see how we can do, or Eastern time. First of all, can you provide pros and cons for variable width segmental construction, particularly for precast or cast in place, with some examples?
Yeah, absolutely. So we do accommodate variable width construction and precast segments routinely. In fact, almost all of our projects do have some degree of variable width. Some of the things you've got to watch out for is how much width you're actually trying to accommodate with that. So one implication is how many types of segment boxes. If you can accommodate the geometry with one segment core, you can minimize the number of forms that you require. And so wing variations at the top deck level are fairly easy to accommodate. That can be done with transverse post-tensioning variations. And so for narrow boxes, you can reduce the number of transverse tenons in the deck. For wide boxes, increase the number of transverse tenons in the deck to get your capacity. And so we've got bridges that'll go anywhere from 30 to 60 foot wide in a single box arrangement. But as you do vary significantly in width, you may end up with different box width. So the actual webs have to separate to provide efficient segment design. And so it's just an implication that you've got to consider is what's the size of the job, what's the variation in width, and how many basically how many box shapes you're creating, which will then drive how many forms you need for a precasting operation.
Okay, and then what are some of the major differences in construction methods between cast in place segmental and precast segmental?
Yeah, absolutely. So the technology is fundamentally the same. We're still dealing with very similar design constraints. Some of the things that are different between cast and place. One is that obviously you're doing that on site up in the air at the girder level, and so access, concrete delivery, all those activities, delivery and reinforcing where the workers are working is actually on site up in the air. As opposed to in a precast arrangement, they're down in a casting yard, either on or off site in a more controlled environment. So certainly an implication there between the two of them. One major difference is you can often, because you don't have handling restrictions, and so that's either transport or handling, is that if you need a longer span, cast in place construction can often achieve longer spans. So we see those going up over 700 feet, 760 feet in span lengths using cast in place balance cantilever construction, because those segments in that condition can be much deeper. Even if it's inland, you can have 38 foot tall segments back at a pier and achieve longer spans.
Okay, we'll go into some design questions. Those first questions were sort of general. But now, what are typical software packages that are used to design segmental bridges?
That's a great question. So the biggest requirement that we have when we look at our design packages is time-dependent capabilities. And so all the segmental designs as we're looking at them need to be able to incorporate the time-dependent properties for the concrete and the steel as we're building the bridge. And so we're trying to build this in real time, especially in precast. The most important thing is that we are creating the shape of that bridge in the precast yard prior to erecting the segments. And so we have to be able to accurately predict what that behavior of that segment's going to be, depending on its age, when it's erected, how long it sits there. So creep, shrinkage, behavior of these segments have to be accurately predicted, so we can cast those shapes into those segments, so that when they get delivered to the site, erected, they end up going together the way we anticipated. Typical packages, I think when you're looking at those, so we've used many that have been within the industry for years. Some of the current ones would be Larsa, Midas. We use Bridge Designer, which is an old standard program, but really the capability RM is another one. Capabilities requiring modeling with erection dependent, time dependent capability.
Okay, and what are the codes and standards that are used for segmental bridge design?
Yeah, so primarily for us, it's AASHTO LRFD. It was the segmental guide spec. It was a separate document years ago. Did get incorporated into the standard guide spec design specification for AASHTO LRFD. And so there are provisions in that that really control the segmental bridge design. There are, it has its own behavior properties, requirements, loading conditions that are unique to segmental construction within within those chapters for concrete bridges.
Okay. And then here's a comment. It says, or a question that came in beforehand. It says, can you comment on the procedures, equipment options, design details based on the Canadian codes? And it mentions CSA code and standards and CHBDC. I think it's Canadian Highway Bridge Design Code.
Right, right. So I can't, and unfortunately, I'm not have not had the experience of working on these projects in Canada. However, we have worked on them internationally, and the procedures are and equipment is universal to the industry, to the type of structure. And so when we see these overseas in other applications, the designs are fundamentally it's a service-based design with strength limit checks, and the equipment is used throughout the world. And in fact, in fact, every application I can think of when we're talking about specialized equipment, that equipment has come from overseas by international companies and is used throughout the world in the same way that we use it here. And so it is a universal solution to universal application that we see across the board. Each jurisdiction or each owner may have certain requirements that you have to make sure you comply with, but general procedures and equipment use is consistent across the board.
Okay. Then a question came in about what are the related codes, standards, any textbooks at all for launching design, the design of the launching?
Yeah, and honestly, that's a great question. It goes back. It's not a common use of segmental construction, and so obviously it shows up in other conditions. I can't speak directly to that. I know my colleague Kira had presented on launching girders with ABC as well, and so you have similar conditions you'd be looking at with segmental construction, in which you're building the bridge and then trying to launch or advance it out across the piers onto the piers. Which, just like any of the construction that we're doing, is checking each critical stage of activity, each stage of construction. Primarily meeting stress limits and conditions as we erect the bridge.
Yeah, they were wondering if there was anything special with the wind speeds and dead loads.
Nothing that I'm aware of that would be unique to launching beyond what is our typical erection criteria, which is generally AASHTO that we're following.
Okay. Then a question came in about what method do you use for calculating the modulus of elasticity of the concrete?
Yeah, so all the properties with modulus, I mean, in general, it's AASHTO, but the modulus, any of the concrete properties are variable, and so we use the CEB FIP code for determining time-dependent properties of our materials. And so that's modeled in each one of the time-dependent programs. And so that's how we capture that is there are model curves that anticipate or predict modulus change, seal relaxation, creep behavior within these structures, and that's the CEB FIP. That had progressed from the 78 code to the 90 code. Now there's a 2010 code that's starting to be used on projects as well.
Okay, I'm going to ask some questions that came in during your presentation. The first one I have here is for the segment that's over the pier. Do you fix it to the pier during erection in the case of balanced cantilever?
So great question. Typically, it is not necessarily, it's not fixed per se, but it is often supported on the bearings. And so a couple important points is those segments directly over the piers have diaphragms in them, and so because you have to transfer that load along the girder down to the bearings, and so the inclusion of the diaphragm is basically that core area is filled. There are access holes through that core area for inspection as you move through the box, but and then because of that, they're usually shorter segments. So what our typical approach in a balanced cantilever can be one of a couple different things. It can be an integral pier, and so it can be the pier is erected. That can be done with a shell, or in some cases we have that directly over the pier can be cast in place. as a transition then to start precast erection off of that cast and place section. Or most common, it's a precast piece, shorter, and we often do them in half length, that then is erected, stabilized on the pier, assembled together, and then the bearings are grouted. And so we usually get what we call the pier head assembly, which is the pier segment itself, and then one or two up and down station segment pairs, just to give you enough length to project out to the end of the cantilever with geometry control. And so you're monitoring that and setting that. And then you're going to grout the bearings in. And so those are rotational bearings. And so the out of balance false work is what provides that restraint to those unbalanced moments. Now, as far as if it's a sliding bearing, these are usually high load multi-rotational bearings that are being utilized. If it is a expansion or sliding bearing, that is temporarily locked longitudinally to make sure that as we're putting load into it, that it's not a condition that then is a slippery surface. We want to make sure and restrain that, restrain those segments and that cantilever to the pier, transfer the load through that mechanism that can accommodate it.
Okay. For the mobile segment lifter, is there a maximum height bridge clearance where this technology can be used?
A maximum height, well, like how far above the ground the segment may be erected, I would think. So we do encounter that a little bit, and it kind of depends on the equipment, because cable hoisting, I know it's being utilized in a project with up to 90 foot of elevation, vertical clearance of the hoisting the segment from the ground up to the superstructure location. Obviously, that can be expanded if needed, because you just got to make sure you got the coil length, the ability in the cable and the coil length to go higher. Yeah, that's kind of the extent of what I've seen is.
Okay, in the case of span by span construction, do you stress the post tension and tendons after or before erection? Or do you tension some of them and then you do them all at the end? What do you do?
Yeah. So if the segment has transverse tendons in the deck, those are all done in the precast yard typically, is where you'd expect to see that. The longitudinal tendons that make up the bridge, so each piece, each segment's is suspended in span by span or supported on the false work. The tendons are then installed once those segments are erected. So that's why they all have to be either hanging from a piece of equipment or sitting on top of a tower, or jacks that are on a underslung truss, is that they can't suspend themselves. So they're aligned, brought together. PT bars are used temporarily just to squeeze those segments together. So there's epoxy that's put between those faces. PT bars are installed, and that squeezes that to maintain that joint alignment for those segments, but it doesn't provide support for those segments. Then once those segments are all assembled, aligned, and any alignment closures, if you have alignment closures, have been completed, then you install your post tensioning cables that will run from one end of the span to the other end of the span, and you will stress those. Typically, to your point, you'll do a limited number of them. And so what you're really trying to do is relieve the piece of equipment that is suspending that. You don't want to add to it. So as the equipment's trying to pick up that span, and you start stressing those tendons, and those tendons are picking up the span, you don't want to duplicate that and create tension in the top. So you'll do a partial span stressing. You'll relieve the equipment to where it's no longer pulling up or pushing up on that span, and then you can perform the remaining span tendon stressing.
Okay, what is the typical thickness of each segment? I think that means the depth.
Well, yeah, so there's two things at play there. So again, depends. So a lot of the ones that we're looking at precast, if they're highway transported, you're typically in a 10-foot segment range, 9 to 10-foot segment range. You can have variable depth. So if you're trying to achieve longer spans, and then, for example, if you've got barge access, we've seen projects with variable depth in which they were 18 feet deep in a precast operation. One of the important things when you look at precast is it's not just the transport, but when you get to the erection site, is the piece too big to pick up? And so you got to make sure that the equipment you have can pick up whatever it is that you cast. So there are some limitations just about how deep you can get. Then when you talk about the structure itself, as far as the thickness of the elements, that can vary as well. But in those typical ranges, you're looking at you've got haunched top slabs, so 1'3" to 9" in a haunch, depends on if you've got cantilever tendons up there. 1'3" in your webs in a thickness, and usually a fairly narrowed 9-10 inch bottom slab, depending again on what type of post tensioning. If you've got
Okay. Could you comment on post-tensioning, stressing, and grouting procedures and equipment in ABC overhead construction, how these influence the overall construction and design?
I can certainly try. I'm not sure exactly what that question's asking, but I mean, so all the tendons as we're being installed require grouting or some protection, and so that's either using cementitious grout, flexible fillers, depending on where you're at, or other replaceable means, depending on what jurisdiction and what the goals are of that particular owner. So grouting operations typically need to follow. There's a duration that after installing the tendons, it's not immediate, and so it's not necessarily required to continue erecting segments. But there is a certain amount of duration that those strands are protected prior to being installed into the segments. Typically, that you can look at a range of 14 days from the time that a strand is installed until it has to be grouted, to make sure that it's protected from the elements. So you don't want to put in steel, have it exposed to elements that are disadvantageous to the material, and then protect it. You want to go ahead and get that protection in. As far as the procedure of grouting, again, depends on the method being used, but the steel strands are installed in ducts. Those ducts have couplers between the segments to make a continuous enclosure for that steel strand, and grouting operations commence from, in most tendons, from one side, injecting the material and pumping it through the length of the tendon out the other side until you get clear flow, and then shutting off that grouting operation and then following up with inspections after that.
Okay, it's about 9 after. I'm going to go ahead and let Jugash come on. And there's a few more questions here. And Jugash, I'll let you do it.
Thank you, Paul. First question, Matt. It's asking, in the case of balanced cantilever method of construction, do you stress the PT bars that assemble segments after or before erection?
So the PT bars would be stressed after erection. So as we squeeze segments together, so each one is brought up individually, and particularly in a balanced cantilever arrangement, you're usually working with one. The most common is the ground base crane, and so you usually have one ground base crane per cantilever. And in doing that, what'll happen is the crane will pick up the first segment being erected of a pair. So you've got a cantilever, it's in a balanced state. You pick up the first segment, and using the crane, bring it adjacent to the previous segment, install the epoxy, and then use a temporary post-tensioning bar from the previous segment to the new segment to squeeze that segment together. And in that application, the bar is actually being used to support that segment. So once those PT bars are stressed, the crane can then release that segment. It is now attached to the previously erected cantilever. The crane can then pick up the balancing segment off the trailer and on the other side of the cantilever and raise it into position, install the epoxy, put it into position, bring it into contact with the previous mated segment, and then stress those post-tensioning bars as well. Once those post-tensioning bars are installed, it releases that segment from the crane, and then your cantilever tendons are installed, which go from one end of the cantilever to the other, connecting, capturing both the segment pairs in that arrangement.
Okay, thank you. Next question. When two cantilevers are constructed from each side and for some reason the last segment does not align or fit perfectly, what are the measures that can be adopted to resolve that? Has there been any experience like this before?
Yeah, so it's something that's very important to monitor. And so a big part of segmental construction is the monitoring of segment erection as you're progressing along the cantilever. Particularly critical in balanced cantilever, because if you get a misalignment back closer to the pier, any misalignment projects along the length of the cantilever. So a small discrepancy back in a pier creates a large discrepancy at the cantilever tip. And so you're tracking segments. One is you're prescribing the geometry to cast those segments to, and then you're tracking those segments as they're cast, transforming that back to coordinates that are used on the erection site, and every segment erected is surveyed to confirm that it's tracking appropriately, and so that you can make corrections early on if you need to. Those corrections are often shimming, on a cantilever. So as if you see something going wrong and it's deviating from what the segments would have been cast to, there are shims you can install in that segment joint to reorient or point that cantilever progression into a different direction. In extreme cases, you can install a wet joint, which is a small joint that realigns the bridge and cast in place. There's obviously a lot of challenges to that on a site, so you try to avoid that at all possible. If you get to the end of the cantilever and those cantilever tips are misaligned, if it's a rotational cantilever, you can use strong backs, rotate that cantilever into a better alignment, create a best fit geometry. You can induce structural deflections if the design can accommodate it. And so that's one of the areas where a more robust design that has some reserve capacity in it can accommodate some geometry adjustment that is a load-induced deflection.
Okay, thank you, Matt. I believe this would be the last question. Who are the main or most common segmental bridge builders and designers in the industry?
That's a great question, and it varies. And so some come, some go. And I'm not sure I can address designers particularly. I think obviously we would consider ourselves in that category, but there are a number of good ones. I do have, as part of the information included here, um, one of the sources, which is the ASME, American Segmental Bridge Institute, has longstanding members, and they are always looking forward to helping folks in the industry get connected with the right people. And so if anybody's looking for resources there and who they can talk to, that would be certainly one of them that would be a good source to reach out to.
Okay, the answers to the outstanding questions will be posted online. I am almost out of time, so I'll turn it back to Kathy. Thank you, Matt, for your answers.
Thank you.
Thank you very much to Jigesh and to Paul for moderating the question and answer period. And a special thank you to Matt for sharing all of the knowledge he's gained in his career. It was very interesting and detailed. We really appreciate your time. And that is the end of our presentation for today. Thank you all for attending.
Thank you.